For decades, the moon has fascinated scientists, and recent Chinese missions have dramatically advanced our understanding, challenging long-held assumptions about its origin, structure, and resources. Traditionally, our picture of the moon was based on the Apollo missions of the 1960s and 70s, which brought back a substantial amount of lunar rock and dust. Those samples immediately revealed something surprising. The moon's rocks closely resemble those found on Earth, indicating a shared origin rather than two independent bodies that merely encountered each other in space. This finding fueled the prevailing hypothesis that a colossal impact billions of years ago, involving a Mars-sized rogue planet colliding with the early Earth, created the moon. The immense energy of this event, often described as the Big Splash, would have liquefied both bodies, hurling a portion of Earth's material into orbit where it eventually cooled into the moon, while the impactor's remnants were largely absorbed into Earth's core. Although widely accepted, this theory remains unproven and continues to face challenges as new data emerges. For instance, simulations run on supercomputers have modeled countless scenarios, yet questions linger about the moon's thermal history. Conventional wisdom suggests that, being much smaller, the moon should have cooled quickly, particularly on its far side, but evidence increasingly contradicts this notion. The Apollo program's achievements were monumental, but the areas explored by astronauts were extremely limited, just 25 square kilometers, barely a fifth of the size of Disney World, mostly restricted to flat equatorial plains suitable for landing. If aliens visited Earth, wandered only through a theme park, and claimed to understand the planet, their conclusions would be equally flawed. Modern exploration, led largely by China, is rewriting the lunar narrative through missions that venture into geologically intriguing regions and return fresh samples. Over the past 5 years, China's space agency has heavily invested in robotic exploration, focusing particularly on the moon's far side, a region perpetually hidden from Earth. Contrary to popular misconceptions perpetuated by pop culture, the far side is not perpetually dark. It receives sunlight like the near side, but never faces Earth. Interestingly, this hidden hemisphere is markedly different from the familiar near side, which is characterized by expansive, dark basaltic plains formed by ancient volcanic activity. The far side, in contrast, is lighter, heavily cratered, and lacks extensive lava flows, suggesting significant geological differences. In January 2019, China's Chang'e 4 mission made history as the first spacecraft to land on the far side, deploying the U-2 rover to explore the Von Karman crater, a vast depression within the South Pole Aitken Basin, one of the largest and oldest impact structures in the solar system, nearly 2,500 kilometers across and almost as wide as India. This colossal basin, formed about 4 billion years ago, likely exposed material from deep within the moon's crust or mantle, a treasure trove for scientists seeking to unravel the moon's interior composition. Indeed, U-2 discovered rocks believed to originate from the lunar mantle, marking the first such finding in history. Apollo astronauts never retrieved mantle material, so this was a breakthrough. Adding to the intrigue, the rover captured an image of an odd cube-shaped object in late 2021, which fueled speculation about artificial structures or even alien artifacts. Ultimately, closer inspection revealed it was merely a rock, its blocky appearance an illusion created by lighting, shadows, and low-resolution imaging. Nevertheless, these missions underscored the value of persistent exploration. China's subsequent Chang'e 6 mission in 2024 returned sample from the far side for the first time ever, allowing scientists to compare its composition directly with near-side material collected decades earlier. Initial analysis revealed stark contrasts. Far-side soil and rocks are lighter in color, more adhesive, and contain larger clumps than their near-side counterparts. Even more surprising was the volcanic history these samples revealed. While the far side was expected to hold the oldest, most primordial material, scientists also found relatively young volcanic rocks averaging 2.8 billion years, significantly younger than many Apollo samples, which are often over 3 billion years old. This suggests that volcanic activity persisted far longer than previously believed, extending the moon's geologic vitality well beyond accepted timelines and challenging assumptions derived from the Big Splash theory. If the moon formed alongside Earth and was much smaller, it should have cooled and solidified quickly, especially on the hemisphere facing away from Earth's lingering heat. The evidence, however, points to a more prolonged molten phase, complicating existing models. Meanwhile, China's Chang'e 5 mission, an earlier near-side expedition, also yielded paradigm-shifting discoveries. It landed near Mons Rumker, a vast volcanic dome, and retrieved the youngest lunar rocks ever sampled, just 2 billion years old, further reinforcing the view that the moon's interior remained active for eons longer than imagined. Lunar volcanism differs from Earth's dramatic eruptions. Instead of explosive plumes, moon volcanoes likely oozed lava slowly through surface weaknesses, creating sprawling, low-profile domes. These insights have profound implications for reconstructing lunar evolution and thermodynamics. Beyond geology, China's missions have unearthed entirely new minerals, expanding our understanding of lunar chemistry. Among the most remarkable finds is Change Site-Y, a previously unknown transparent crystal that contains helium-3, an isotope touted as a potential game-changer for future energy production. Helium-3, deposited on the moon by solar wind and virtually absent on Earth due to our protective magnetic field, could theoretically fuel nuclear fusion reactors, offering near-limitless clean energy without the radiation hazards or long-lived waste of conventional nuclear power. While practical fusion technology remains elusive today, helium-3 positions the moon as a strategic energy resource for the future. In addition to exotic minerals, Chang'e 5 detected water molecules embedded within a hydrated mineral, overturning earlier assumptions that lunar water existed only in perpetually shadowed craters near the poles. This suggests water may be far more widespread and accessible than thought, bolstering prospects for sustaining human outposts virtually anywhere on the surface. Water is indispensable, not just for life support, but also for generating oxygen and producing rocket fuel, making it a cornerstone of any permanent settlement. China's lunar endeavors are not merely academic. They represent a deliberate strategy to pave the way for long-term human habitation. Unlike the Apollo era, when astronauts stayed briefly and operated under minimal infrastructure, future lunar bases demand exhaustive reconnaissance. Robots scout resources, analyze hazards, and map potential sites for habitats and power systems. The discovery of young volcanic rocks, hydrated minerals, and helium-3 all underscore the moon's complexity and promise. Meanwhile, comparative studies between the near and far sides reveal that our celestial neighbor is anything but uniform, with a geologic story far richer than imagined. The more we probe its surface, the clearer it becomes that the moon is not a static, dead relic, but a dynamic world with secrets still locked beneath its regolith. These revelations not only rewrite the moon's history, but also illuminate Earth's own origin. For in deciphering our satellite's past, we glimpse the violent, chaotic processes that shaped the early solar system. From the first human footprints to the latest robotic wheels, the quest to understand the moon remains one of humanity's most ambitious and consequential scientific journeys. And as China leads the charge, the next chapter may well redefine our future on two worlds. Looking ahead, the next phase of lunar exploration promises to be even more transformative, as China accelerates plans for a permanent presence on the moon, while other nations, including the United States, Europe, India, and Russia, intensify their own efforts. The Chang'e 7 and Chang'e 8 missions, scheduled for the latter half of this decade, aim to establish the technological foundation for a sustained lunar base, focusing on the resource-rich South Polar region, a place of perpetual sunlight on certain peaks, ideal for solar energy, in proximity to shadowed craters that may harbor vast reserves of frozen water. These missions will test critical infrastructure, such as autonomous construction systems, 3D printing technologies for building habitats from local regolith, and closed-loop life support systems capable of recycling water and oxygen, all essential for minimizing dependence on Earth. If successful, these steps will enable China to assemble the International Lunar Research Station, ILRS, by the 2030s, a project envisioned as a multinational outpost, rivaling the International Space Station but fixed on solid ground, serving both scientific and industrial purposes. Such ambitions are not purely exploratory. They're strategic, driven by the recognition that lunar resources, particularly helium-3 for fusion energy, rare earth elements for advanced electronics, and abundant oxygen locked in the regolith, could underpin a new era of space-based economies. Meanwhile, NASA's Artemis program aims to return humans to the moon by mid-decade, with an eye toward establishing a sustainable presence and using the moon as a springboard for missions to Mars. This emerging competition and potential cooperation herald what some call the second space race. But unlike its Cold War predecessor, this race is not about planting flags. It is about securing long-term access to extraterrestrial resources, developing new technologies, and shaping the future balance of economic and geopolitical power beyond Earth. At the same time, these developments raise profound questions. Who owns the moon? How will space law evolve to govern mining rights, territorial claims, and environmental preservation in an uncharted domain? The coming decades will likely witness the drafting of new international treaties and perhaps even the creation of a lunar regulatory framework to prevent conflicts and ensure fair access. Yet the stakes are so high that friction seems inevitable. As robotic and human missions proliferate, we may also uncover evidence of processes that challenge our understanding of planetary science, or, in the most speculative scenarios, hints of life's chemical precursors preserved in ancient volcanic glass or cometary deposits. Every new drill core, every sensor reading from orbit, brings us closer to answering questions not only about the moon but about ourselves, how life began, how planets form, and how humanity might thrive beyond its cradle. In this context, the moon is no longer a silent satellite hanging in the night sky. It is a gateway to interplanetary civilization, a proving ground for technologies that could one day sustain settlements on Mars or even more distant worlds. Its dusty plains, once a symbol of isolation and stillness, are fast becoming the frontier of a bold and uncertain future, where science, ambition, and survival converge in ways that will define the next great chapter of human history.